This video is going to look at the 1 and 2 star questions for chapter 3 of Walding. As there's not too many, I reckon we can do both in one set of videos. So let's get started. Question 22. Find the magnitude and direction of the resultant vector obtained by adding displacements of 4 meters east to 6 meters west, velocities of blah, blah, and a couple of other things. So we've got a whole bunch of different vector quantities there. So let's start drawing them out. So 22A, we have displacements of 4 meter east. And we have, we have a vector of 6 meters west. So from here going back the other way. Now, by convention, we say that east is to the right, west is to the left. You can swap it around if you really want to. If you want to do something other than the typical convention, draw me a compass rose so that I can see what you're trying to do. It's part of those communication things. However, we can just assume the convention. So the resultant vector in this case is the distance when we're adding them from start to finish here. Now, if we drew this accurately, we could then measure that, and we would find it would be 2 meters. Put that in red. 2 meters to the west. However, I'm not drawing this accurately, so let's try to confirm it mathematically. So 4 meters east plus 6 meters west. Well, we want to turn that west into an east, or west is a negative east, so that's the same as 4 meters east minus 6 meters east equals negative 2 meters east. We just said negative 2 meters east would be the same as 2 meters to the west, which is what our picture shows. Okay, B. Velocities are 5 meters per second east and 5 meters per second south. So we have 5 meters per second plus 5 meters per second. And notice I am adding head to tail, and so we are trying to find this vector. That would be our resultant of adding them together. Now we can see here we've got, if this is east and that's south, that has to be a right angle triangle, and as we should remember, adding vectors at right angles requires Pythagorean theorem. We will also require an angle for it. Let's see if the answers are chasing it. 21, 22. Yes, we are chasing it. What I can tell you though, because this is kind of a trivial angle to work out, that angle, if these two are going to be the same, we know that the angle must be 45 degrees. Okay, that's a nice little thing just to keep in mind, so that you don't have to waste time on math you don't need to do. Now let's work out the hypotenuse here. So we know that our resultant vector, the size, is going to equal the square root of 5 squared plus 5 squared. We just rearrange Pythagoras. So square root of 5 squared plus 5 squared would be 50. So square root of that would be just over 7. Square root of 50 gives me, close to 7.1. So in total, our resultant here, I'm just using R for resultant. Don't forget, your vector needs a hat. 7.1 meters per second. Don't forget the units. Now that angle there is east, 45 degrees south. We could do whatever 360 take away 45 is, so 315 degrees would be our positive Cartesian or polar coordinate all the way around. Or we could go negative 45 degrees would also be appropriate, but they gave it to us in east and south, so let's give it back to them in east and south. Accelerations are 3.2 meters per second north and 4.8 meters per second west. Well, that's going to be the same as this previous one, which was for numbers that have a little bit more varied, and we've got some different units, but the units don't matter, and the directions are not doing much either. Meters per second squared. Again, in this case, we need to work out our resultant vector. So now we're going to have to do a little bit more algebra to work out this angle of theta. So R is going to equal square root 3.2 squared plus 4.8 squared. Let's check that in. 3.2 squared plus 4.8 squared. Take the square root of the answer, we get 5.77. Let's go just 5.8 meters per second squared. Now let's work out the angle. Now when you're working out an angle for combining vectors back together, we're generally going to use tan. We could use cos or sine and use our hypotenuse we just worked out, but there's some rounding error in that, so let's not do that. Theta in this case will equal the arctan of opposite over adjacent, 4.8 over 3.2. I note I am skipping through some rearranging. If you need to write down the individual steps, please do. However, part of improving your mathematics is to be comfortable with just skipping past some rearrangement that you should be able to see without necessarily having to write it down. And the arctan of that is equal to 56 degrees. Okay, and we see that's 56 degrees to the west from north. So our r vector equals 5.8 meters per second squared with north 56 west, or we could go 146 degrees would also be appropriate if we went from the positive x-axis. Last question, displacements of 5 meters west and 5 meters northwest. A little bit more complicated. Oops, sorry, 5 meters west that should be. So 5 meters west, 5 meters northwest, and we want to again find out the resultant. A couple of ways we could work this out. If you drew this accurately, drawing would really speed up this a bit. So you could work out the angle in here by drawing it, and you could work out the length by measuring it as well. We could break this down into how much to the west. I'll draw those lines in. We could work out how much this goes across, and then how much this goes up, and then we would then work out, okay, well that and that would give us the hypotenuse for our red line. I'm just going to do the cos and sine rule. Remember, I do expect you to be familiar with it. So we're going to work out this side of our triangle. We're going to need to eventually work out this angle, and we need to know this angle in here. Now, if this is northwest, so I'll just dash that up a bit. If that's northwest, that has to be 45 degrees. That's something that you should assume to know. And here, if that's, say, north, because that's northwest, then that has to be 90 degrees. So that interior angle there, we'll call that phi for the moment. Phi is going to equal 135 degrees, 90 plus 45. So we're going to use our cos rule to work out our missing side of the triangle. So let's go that c squared equals a squared plus b squared minus 2ab cosine of, in this case I want to use phi because that's what the symbol I gave that. Yeah, I could use theta, it's just a symbol, don't super stress. So c squared equals 5 squared plus 5 squared minus 2 times 5 times 5 times the cosine of 135. Alright, let's put all that in. So 5 squared plus 5 squared is going to be 50. Let's work out that cos of 135. In note we do get a negative, but that's okay, times 5 times 5 times negative 2. And we're going to add that to 50. Not times, add that to 50. Then we'll take the square root of that, and we'll get that c equals about 9.2 meters, which looks reasonable. Now we want to work out that angle in there. We can use the sine rule for that. So the sine of theta over 5, which is the side opposite, equals the sine of 135 divided by 9.2. So if we rearrange that, theta will equal arc sine of 5 sine 135 divided by 9.2. So sine of 135 times 5 divided by 9.2. Take the arc sine of that. We get that it is equal to about 22.6 degrees. So our final vector equals 9.2 meters at, well, this is starting west and going north, west, 22.6 degrees north. Okay, next step. Calculate the following, add that plus that plus that, add that plus that plus that. Okay, so it looks to be very similar to what we just did before. However, now we've got some 3 sets of vectors, we've got some with some decomposition being added, and we've got some with subtraction as well. So let's have a weight in here. So our first one, we have 15 meters north plus 23 meters west, so a little bit longer, plus 20 meters south. Okay. Now let's write that as a sum: 15 north plus 23 west. I know I've skipped the units, but they're all the same unit, so just add it in at the end. Was 20 south. So south and north are going to be opposite of each other. We're going to end up with 23 west plus 5 south. It's important to do as addition, because addition allows you to draw it. Subtraction, while it works, is a little bit more annoying. So you could have written minus 5 north, but you'd have to draw the same thing anyway. This just makes it a little bit less ambiguous. So our final vector is going to be 23 west, 5 south. Alright, do we want the size? Probably want the direction as well. Let's double check. Yep, wants the direction as well. So our resultant vector is going to equal the square root of 5 squared plus 23 squared. Which gives us 23.5, because 5 squared does not add much to 23 squared. And we want to work out this angle in here. Theta will equal arctan of 5 over 23. Is 12.3 degrees. So to be that R equals 23.5 at west, 12.3 south. On to the next. 20 meters east, 15 meters north, 15 meters north, 30 degrees east. Okay, so this one, you could be thinking, oh, it's like before we used our cosine and sine rule, but let's see why that won't work here. So 20 meters east, 15 meters north, and then 25 meters north, 30 east. That should be a bit longer, maybe. And so again, we're trying to work out our resultant, which will be from here up to there. Note, my drawing is definitely not to scale. But we do need to put in that 30 degrees. It's not a triangle, and that's a problem. We could make it a triangle by working out, well, how long is this line going to be by using these two, and then using that bigger triangle to work out that. But generally it's going to be easy to break this down into how much east and how much north, and then put it all together. So let's work that out first. So how much east there is and how much north there is. So I'll just redraw this vector for a moment. 25. We know there's 30 degrees, so we can see here that the north is going to be cosine. It's adjacent to the 30 degrees, and the x value, the east value, will be opposite. The textbook does say always use cosine to work out x. No, if you draw it like this, it's not going to bloody work. You have to be intelligent, you have to think about it. So our x here is going to equal 25 sine 30, which means our y here will equal 25 cos 30. And if you can't see how I got straight to that, you need to be practicing. Sine 30 is a half times 25 gives me 12.5. cos 30 is a stupid looking number, times 25, gives me 21.7, just about. So that's how much north there is, that's how much east there is. So let's put them all together. So our total of north equals 15 plus 21.7. Our sum of east equals 20 plus 12.5 equals 32.5. So that's going to be our north, that's going to be our east. So now we've got two numbers we can use to work out 32.5, 36.7 to work out that and that, and I will leave that to you because I've shown you the tricky part of this. Okay, C, add 5 kilometers northeast, 20 kilometers south, 15 meters east. That one is identical to the one before, so I'll draw that up. So 5 kilometers northeast, that will be 45 degrees. That's maybe slightly tricky. Just remember that if it's a northeast, northwest, that sort of thing, that's 45 degrees. You can do it on either side though. We've got 20 kilometers south, and then it was 15 meters east. Oh, we've got a lovely unit swap there. So we could turn this into 20,000 meters and 5,000 meters. I mean, that 15 meters is going to be next to worthless. Calculate it with the meters. You can see here you're going to have to break this down, and then you can add all the east together, and you can add the north against the south. However, if the number comes back very wrong and just got to follow the same process I did in B, it may have meant to be 15 kilometers east, because that seems like a really weird shift all of a sudden. None of the others have these unit changes, so it may have been meant to be 15 kilometers instead, but I'll leave you to test that out. I'm going to do D quickly. We have here, I'll write this as a sum first, 20 north minus 18 north. This one's going to be pretty trivial. So when we are subtracting it, what we're doing is adding the opposite vector. So I'll draw that out first. So 20 north, so 20 north, and then we're going to take away 18 north, which means instead of adding on, I'm going to take it the other direction. And we should see here that that's going to equal 2 north, isn't it? Not a particularly difficult one there, and there's no angle either. Okay, let's move on to question 24, our first 2-star question for this group. So, what is the change of velocity when a tennis ball travelling at blah is hit directly back at a speed of blah? Alright, so we want change of velocity. Technically it's a vector, or velocity is a vector, so we could draw this. So let's say that originally we have, it's going to be built to finalize filtering issue. But let's draw it first. So 80 kilometers, let's say that this way at 80 kilometers hits back. Okay, so we want to have the difference of it. The second vector then is the opposite direction. Oh, that was horrible vector. At 95. No, this is not adding, we're just next to each other. So a subtraction, because that's what we want to find. This is our VI, this is our VF. We could just put that in there, but we want to draw it as well. A subtraction is the same thing as adding the negative. So adding the negative means I flip it. So this would equal, so this take away this equals 80, 95, which means that we're adding it together, so we should get 175 meters per second. This is the delta V. Let's see if that works on the math part. So VF is 95 kilometers per hour, so not meters per second, kilometers per hour. But it's going one direction. Do we we make it positive? Do we make it negative? Let's make it positive. So 95. Take away. Now we can't do take away 80. We'd get 15. And that doesn't match what we've got over here, so that would be something, one of those two would be wrong. If this is positive to the left, this has to be negative to the right. Take away 80. Now we've got 95 plus 80 equals 175 kilometers per hour. Okay. B. A car travelling north at 45 kilometers an hour turns west and travels at 60 kilometers an hour. What is the change in velocity? So again, change in velocity means we're taking a subtraction. Okay, so we want to know what is the difference between start and finish. We have here VF equals 60 k per hour west, VI equals 45 k per hour north. So that means if we can't really do this because it's they're not in the same line, so we can't do it by definition of difference. So we're going to have to draw it and then see what we do from here. So what we're doing is VF take away VI, which is exactly the same as VF plus negative VI. And we can add vectors. We know how to add vectors. So our first vector VF, let's draw that, 60 k per hour west plus negative VI. So VI is originally going north. VI must be going south, or negative VI must be going south. And now we can see, yeah, it's just a right angle triangle. I'm going to use my Pythagorean theorem and my compass directions to work out how long that is and what the angle is, which I think you can do from there. C. A cricket ball strikes the pitch at a speed of 30 meters per second at an angle of around 28 degrees, bounces up at an angle of 35 degrees at a speed of 25 meters per second. Same sort of thing, just a little bit more complicated. So let's start off with our initial. So VI equals 30 meters per second. And we are going at an angle of 28 degrees off the ground. So I'm just going to draw the vector just to help us see that, because we haven't really covered up-down directions. So I could say 28 degrees to the horizontal or into the horizontal, or I could go all the way from positive horizontal. It's just kind of annoying, so let's just draw it. And we say that its final is 25 meters per second. And let's put an arrow on there because that's the direction. And the direction will be 35 degrees. Okay, we can do the same thing. We're looking for a difference. So we're going to draw our two. So we want negative VI, which means we're going to have to reverse the direction. So we're going to have originally 25 meters per second. That'll be our first one. That's our vector final. We're going to add the opposite. So it's going to go up like this instead. Okay. Still coming up at 28 degrees from the horizontal. And it will be at 30 meters per second. Now, if that angle here is 35, then by Z rule, that will also be 35 degrees. And being as we want the resultant vector, we can see here we've got something similar to the cos rule again, where we have our anterior angle, we have our opposite side we want to find out about, and we have our two shorter sides of the thing. And then we can use the sine rule to work out this value in here. Note that you'd have to add it to this 35 to actually get how far from east, so east some amount north, to get the actual angle. But I think once you see that drawing, that's the tricky bit, and you should be okay from there. Okay. A 4.5 gram bullet travelling west of 700 meters per second strikes a piece of armour plate and is deflected by 40 degrees off course with a 20% loss in speed. To do the same thing. The fact that they've given us a mass is kind of just a sort of trick to make you think about, oh, do we need something with that mass? Nope, it's just there. So we started off at 700 meters per second. to the west, so that means our vector initial equals 700 meters per second west, and then it struck this sort of armor, let's just draw it as a circle, and then bounces off that way with 20% less speed, so 700, oops, that's 80% of 700, would give us 560. And in this case, if that's west and that's deflected by 40 degrees, then that's going to be north 40 west. So VF equals 560 meters per second at west 40 north. Again, we're going to do VF, take away VI. So let's draw our VF, which is the same thing as VF plus negative VI. So we've got our first vector, the final vector, 560. It's a terrible 560. 560 at 40 degrees. And we want to add to it negative VI. So VI is originally going that way, so negative VI is going to be that way. So that's going to be 700 east this time. And again, we can see, alright, well, what's that from there to there? Now, sometimes drawing these, you might look at it and go, well, that doesn't make sense. Why is it that way? Let's think of the difference between this to this. If I have a look at these two vectors, and I want to compare them, so the amount going to the left has been shortened, not only because it's turned up, but also because it's slowed down, which means I need some vector going back to the right. This part here had nothing to the north, this bit had some to the north. So not only do I need something going to the right, but also need it going up in order to push it in that motion. Hence why our resultant vector is kind of this non-intuitive idea there. So keep this bit in mind, that subtraction is the same thing as just addition of the negative. And negative means we flip the direction. We don't change the signs, we're just flipping the direction. Then draw your vector addition like you normally would. Start to finish, trust the math, you'll be okay. Okay, 25. This is a question that probably should have been earlier. What are the north and east components of, well, we've got a couple of different values there. So here they want you to use the sine and cos rule to work that out. So for 100 kilometers north, well, it's going to be 100 kilometers north, 0 kilometers east. I think that one should be pretty simple. Let's go to B, 50 meters per second north, 30 east. So let's draw that. We'll go north 30 east at 50 meters per second. We can see here the north component is going to be the cos, the x component or the east component is going to be the sine. So we're going to have the north bit equals 50 cos 30, and then the east bit is going to equal 50 sine 30, which equals, so that should be 25 cos of 30 times 50 gives us 43. 43 north, 25 east. And the last one there, we have 25 newtons at north, 40 east, same thing as before. That one's really no different to this one, it's just that we've got a slightly different angle. 40, and we have 25 instead. So our north is going to equal 25 cosine of 40, our east will equal 25 sine of 40. Okay. 26. A man can row a boat in a northerly direction of 5 meters per second relative to the water across a river 300 meters wide. A current is flowing due east of 12 meters per second. What is the velocity of the boat relative to the ground? So when we think about this, we have two vectors. They are adding together. Now the man relative to the water is just going 5 meters per second north. He's not trying to move east with the water, he's just moving north. However, relative to the shore where he started, not only is he moving 5 meters per second away, going across the river, but then the river is following him down at 12 meters per second. So this is an idea of relative velocity where we need to be thinking about vectors. so let's draw our vector situation. We have 5 meters per second. Excuse me, 12 meters per second. We can see, oh yeah, I'm going to be using Pythagoras here, and I'll have to work out the angle. So resultant will equal the square root of 5 squared plus 12 squared, and the theta will equal arctan of 12 over 5, and I'll just skip straight to the answer for that. We see for 26, 25, 26, 13 meters per second, and the angle will end up being 67 degrees. So that would be north, 67 east. Okay, B. What time would it take to cross the river? Now, the fact that it's going down the river doesn't matter. Remember, vectors at right angles don't interfere with each other. If it's, we're going to here use a basic velocity equals displacement over time. We know his velocity is 5. We know his displacement has to be 300 to get across. So we want to know the time. So time equals S over V equals 300 over 5. Should be 16. Yeah, equals 60 seconds. How far downstream would the man land on the opposite bank? Well, while he's going across, taking 60 seconds to do so, the river's also pushing him down. So same formula, but now we're going to use S equals VT. The V in this case is 12 because the river is what's carrying him down. And he's carrying him down for 60 seconds. Gives us 720 meters downstream. 27. For figure 3.33, show by means of a sketch how you would add the two vector quantities, subtract, and then multiply. Okay, so similar to what we did before, just we've got our vectors drawn. So subtracting A plus B, that's vector A, that's vector B. Done. Okay, add the two, subtract vector A from vector B. Okay, so we're doing B take away A, which is exactly the same as B plus negative A. Okay, and if A is going up to the right, it's going to, negative A is going to come down to the left. So B, and then negative A. Finally, C, 3, multiply B by a factor of 3. Well, if this is B, and I made it shorter there, then we're just going to draw 1, 2, 3 lengths. We're just making it 3 times bigger. 28. Plot a graph to show the relationship between heat and joules. This exam is not testing that, so we're not going to stress about that. However, what you'd be doing there is plotting it, use some of the skills up above in order to see, like, is it a straight line when you plot this? It does say heat developed by current, so current will be on the x-axis, heat will be on the y-axis. I'll write that down. So heat equals y, current equals x, but say chuck it into X or chuck it in your graphics calculator, see what the graph looks like. If it's a straight line, great, it's a linear relationship. Then the next bit is same thing, we're going to be plotting it, so we don't need to worry about that. Okay, so 28, 29 is not relevant to the current stuff we are worrying about. Hope that helps with some things. If you've got questions, do check the earlier stuff, and otherwise ask in class. Have a great day, guys. Bye.